All right, so we've talked about stretches, we've talked about bends, we've talked about now torsions. Let's talk about the other terms in the force field. One of them is the van der Waals energy. In chemistry, van der Waals forces or van der Waals molecules have to do with energies or systems that exhibit van der Waals interactions, which means weak, non-covalent interactions, non-bonded interactions between molecules. So if I have liquid water and I have two water molecules that see each other, you could call those van der Waals interactions the attraction of one water to the other water molecule, or sometimes repulsion, depending on how they're lined up. If the two oxygens are near each other, it'll be repelling each other, but if oxygen is interacting with a hydrogen, then it can be attractive. So it depends on the geometry and situation, but they're basically interactions between molecules that are typically weak, or at least not as strong as a covalent bond anyway. What do these look like? Well, at short range, if you take two molecules or two atoms and put them too close to each other, they'll just collide and they won't like that. So that's repulsive. But at intermediate range, maybe 4 angstroms, something like that, this can be an attractive interaction. And at long range, eventually the attraction goes to 0 because the things are just too far apart to interact. Ultimately, the source of these interactions is either electrostatic type interactions, which in force fields we're going to lump into a different term, so we'll talk about that in a minute, or a so-called dispersion term, or London forces. And London forces have to do with instantaneous dipoles on some molecule inducing a complementary instantaneous dipole on the other molecule. So instantaneous dipole, induced dipole kind of terms. These have to do with electron correlation, correlated motions between electrons. We'll talk about that in discussions of electron correlation methods. But for now, we'll just call them London forces and say these are things known in the chemical literature, and ultimately they're due to correlated motions between electrons. But the force field methods don't actually have electrons in them, so we just kind of make up this term and call it a dispersion term or a van der Waals term, and it sort of lumps in that effect at long range, and at short range it handles the repulsion that you get. Sometimes organic chemists would call this steric repulsion, and sometimes the more physical chemists might call it exchange repulsion, but that's what's happening at short range. How are we going to write down a function that captures all the stuff I just described on this previous slide? Well, at long range, it turns out, we know from various studies, experimental studies, theoretical work, that this attraction is proportional to 1 over r to the 6th, if r is the distance between the atoms or the molecules we're talking about. There's some constant, I'll call it E on this slide. Maybe that's a bad letter because E can sometimes mean energy. Here I just mean some constant E. I'll put it as negative because in chemistry, negative means attractive, things that lower the energy. So that's a good term, a stabilizing term. And then there's the short-range repulsion, so that's the other term in equation 9, C times e to the minus dr. C is just a constant, D is just a constant. So I've got an exponential multiplied by some constant, where again r is the distance between the atoms we're talking about or the molecules we're talking about. In force field methods, usually it's atom-atom interactions we're really discussing. So at short range, then you do this exponential. Eventually, in the limit that r goes to 0, which we would never quite get to, of course, you'd have fusion of two atoms if that happens, so that's not going to happen in reality or in your simulation, hopefully. But in the limit that r goes to 0, e to the 0 is 1, but it's multiplied by c, so you'd get this repulsive term, whatever c is. So you might imagine c might be kind of a big constant. And then, of course, as r gets big, e to the minus dr becomes very, very tiny, and so that first term goes away. So you get a short-term repulsion between the two atoms if they get too close, which goes up to a maximum of C, whatever that is, and then it dies off very quickly. So if the atoms get a little bit far apart, then that repulsion goes away very quickly, exponentially. And then you have this attractive part, minus E over R to the sixth, and that decays kind of slowly. So it's not until the atoms get quite far apart that eventually the attraction goes away. And you can see if I add a short-term repulsive thing to a long-range attractive thing, I would get a nice sort of van der Waals curve. That gives me a minimum at some intermediate range where it's attractive, and that fits the chemical situation. So this is a pretty good mathematical functional form. It's not perfect or super accurate, but it's quite reasonable. Now, one thing I mentioned in this slide that I haven't said so far is that you don't do equation 9 for atoms that are actually bonded to each other. All of these effects are like lumped into the stretching term, and I don't need to add them as a separate term. Same thing if I'm in a bond angle, like in water, the two hydrogens, or hydrogen and oxygen, none of those I include this van der Waals energy for, because those are like lumped in already to the bending term. In fact, I need the two atoms that we're talking about typically to be at least in a 1-4 arrangement. If you imagine 4 atoms all connected to each other, A, B, C, and D, I wouldn't consider the van der Waals term unless I was at least a 1-4 interaction, or maybe I don't even include those. Maybe it has to be, bigger than 1-4, because otherwise it's in the earlier terms we discussed. Okay. I should mention that the computational cost of computing the van der Waals term can be significant because there are a lot of atoms in a molecule, especially if it's a big molecule, that would be beyond a 1-4 interaction. Okay, so many pairs of atoms. In fact, the number of atoms that are actually bonded that I exclude is a small number. For any atom, I include nominally almost every other atom in the system. So suppose I had 1 million atoms. For every one of those 1 million atoms, I include all the other guys. The only ones I drop out are the ones it's bonded to, and maybe the ones in an angle or possibly a torsional angle, which is a small number. So for the most part, to a good approximation, every atom I have to compute the van der Waals interaction with every other atom, and if I had 1 million atoms, I'd have 1 million squared. Now I don't double count. 1-3 is the same as 3-1 or whatever. So it's 1 million squared divided by 2, but still, it's a gigantic number. So this dominates the cost of the calculation, or it can. And we need to speed it up. So unfortunately, that functional form I just told you was quite reasonable and pretty accurate. We don't use it because it involves an exponential, and we just talked about how exponentials can be a little costly on a computer, and if I had to do a bunch of them, like 1 million squared of them, it's too costly. So what we do sometimes is use a simpler functional form, and this one is very famous and very commonly used. It's called the Lennard-Jones potential, and it looks like this. Epsilon is the well depth, and then R0 is the best distance between these two atoms according to the van der Waals potential, and then R is how far apart they actually are. So I compute R0 over R, and I multiply, I raise that to the 12th power. Where does 12 come from? Well, it comes from the fact that I already need this other term, R0 over R quantity to the 6th. That's that London dispersion term we just talked about. I said long range it goes as 1 over r to the 6. So that part we kind of keep like on the previous slide. And then the repulsive part is supposed to be an exponential, and we say exponentials are expensive. I don't want to compute an exponential. You know what? I already computed r naught over r to the 6 because I needed that for the London dispersion term. So let's just square that. And I'll get r0 over r to the 12th, and that will be strongly repulsive. As r gets very, very small, that will rise very steeply. Does it rise exponentially? No, it rises as 1 over r to the 12th. But we'll pretend those are the same thing, even though they're really not. At least it rises steeply anyway. And that is easy to compute because I just take r naught over r to the 6, which I already computed, and I just square that. So the computation becomes cheaper. And if you do a little math, you can see where the epsilon and the factor of 2 come from. This is just kind of a inspired by the previous graph, and it's been rearranged a little bit. All right, so let's see how accurate these various functional forms are. We'll take an example again from Jensen, where I'm looking in this case at the interaction between a H2 molecule and a helium atom. Now, they don't have much attraction to each other, okay? There's not a dipole moment on H2, there's not a dipole moment on helium, there's no dipole, dipole, dipole-induced dipole, there's nothing like that. There's no charges, they're both neutral. So all they have is this London dispersion interaction at long range to make them attractive, which is correlated motion of electrons, instantaneous dipole-induced dipole. If they get too close to each other, they smash into each other and they have exchange repulsion or steric repulsion. So this particular graph illustrates a wide energy range. So you can't actually see the minimum in the potential curve because it's very tiny compared to the scale of this graph. But nevertheless, this will be instructive. And the x-axis, just how far apart is the helium to the H2. So the ab initio points, ab initio quantum chemistry, these are going to be accurate calculations in dots. And there's some tiny minimum in the potential you can't see, but you can see that at long range, the interaction is basically 0, and it stays 0 until they get pretty close to each other. There's some minimum that then is too small to see on the graph. And then when they get too close to each other, they smash into each other, and the energy goes way the heck up. And you can see that dot at about 1 angstrom is at, what is that, about 130 something kilocalories per mole. So it hates to be that close. It's never going to get that close. You can see there's a solid line, the Morse potential. That's the same function we talked about as for bond stretches. Nothing would stop you if you wanted to steal that function and try to make it apply to van der Waals interactions. You could, and it's pretty darn accurate. But in fact, nobody uses a Morse potential for these kind of interactions. They could use either the Lennard-Jones, which is very popular, or this exponential 6, which is quite reasonable, but not so popular because it involves an exponential, just like the Morse does. So let's compare those two. The Lennard-Jones is the fine dashed curve, and it's fine at maybe, I don't know, 2.2 angstroms or more. It gives a very small interaction energy. It's a good agreement with the ab initio curve. But at shorter distances, it rises way too fast. So it's going to prevent the molecule from getting as close as it might in reality, which is inaccurate. But unless you have a high energy, the molecule won't really want to get close anyway. So you're just sort of overestimating how quickly it is repelled, which, depending on what you're doing, may be not great, may be terrible. The exponential 6 is the other dashed curve that looks a lot better at 2 angstroms, 1.75, 1.5 angstroms. It matches that 1.5 angstroms ab initio point pretty well. It rises up the way it should, so it's repulsive. It rises a little too fast, so compared to the 1 angstrom distance, it is overly repulsive, so it's not super accurate either, but it's much better than the Lennard-Jones. And eventually it does a wacky thing where it turns over and becomes attractive at about 0.75 angstroms or less, it turns over. And that's completely wrong. I mean, it's what the function does, but it's not reality. You would, if you used an exponential 6 function, you would need to modify your computer program to check if they got so close that this turnover happened, and if they did, just maybe put in some arbitrary big number or something and prevent that from happening, because otherwise in the simulation the atoms will try to fuse together, which is completely wrong and non-physical. So you can see that there's a lot of ways to get this wrong. Really, the Morse potential is the only one that works for these very short distances quite well, and it's one that nobody uses. The Lennard-Jones is the popular one, and we'll just have to keep in mind that for short range contacts, it's overly repulsive and not super accurate. All right. The electrostatic energy then is the last major term I need to talk about. And this is not the same as the van der Waals energy. It's different. It has to do with the interactions between charges. If I have charged particles, charged atoms, what is the attraction or the repulsion? And we just use Coulomb's law. So in physics, you learn that Coulomb's law tells you the attraction or repulsion between two charges. We just use that here. You have a product of the charges. If you have atom A and atom B, we'll call the charges QA and QB. And Coulomb's law tells you the energy is the product of the charges divided by 4 pi epsilon naught times the distance between the charges. And here, rather than 4 pi epsilon naught, we're just using a generalized epsilon, where that's an effective dielectric that might be tunable depending on what solvent you're in, for example. Okay. How to pick epsilon is a little bit of an art. In fact, sometimes people do kind of a wacky thing called distance-dependent dielectrics, where they say epsilon equals epsilon naught times the distance between the atoms. There's not really a physical justification for that. It's convenient to try to make the interaction die off quicker, and you could wave your hands and say something about screening by solvent or something to try to explain why you're doing that, but basically it's a way to try to turn these interactions off quicker. You'll see that in the literature sometimes. Epsilon would be 1 in a vacuum. All right, so you do this between all the pairs of atoms. Well, not quite all. Again, if they're bonded to each other, you don't do this because that's already wrapped up in the bonding term. And if they're in a bond angle, you don't do this because that's wrapped up in the angle term and so on. But you do it for longer range things. You don't have to do it the way I had on the previous slide. That is the most popular way. But I should mention in the MM2 and MM3 programs, for example, instead of Coulomb interactions between atoms, you use Coulomb interactions between dipoles. So if I have a bond dipole between atoms A and B and a bond dipole between atoms C and D, then those bond dipoles interact with each other, and you just work out the electrostatics of dipole-dipole interactions. And that form is known. In fact, here's equation 12. This is a very reasonable thing to do. It's the product of the dipoles divided by epsilon again. That's still there. But if dipoles interact, the distance dependence is now 1 over r cubed instead of 1 over r. And then it depends on which way the dipoles are pointing. So if I have like 2 dipoles that are pointed in the same direction, that's bad because I have, say, plus charges next to each other and minus charges next to each other. But if I do head to tail and they're next to each other, that's good because I have plus near minus and minus near plus. So the angle matters, and I have to throw that in. Okay, so I can do that if I want. Most force fields will do what we did on the previous slide and just worry about the charges. Now let me say, even though the electrostatic term depends on charges, there is no such thing as charges, atomic charges anyway. electrons have charge, nuclei have charge from the protons, but atoms don't necessarily have a charge if they're in a molecule, because how do you define in a molecule what the atom is if you're talking about the nucleus and the electrons around it? If I've got a big electron cloud, and we know from quantum mechanics electrons are uncertain in terms of where they are, and we describe those with orbitals that tell me how likely it is an electron is here or there or wherever. If I have an electron smack in between an oxygen and a hydrogen in a water molecule, which atom does it belong to? I don't know, who knows? There's no definitive, universally agreed upon answer to a question like that. And so these atomic charges then become a bit of a mathematical fiction. But a useful fiction. So we still want to think about them, even though the definitions are not always clear cut. Okay, one way to define the atomic charges is given through equation 13. So equation 13, what that does, it calculates the electrostatic potential energy at some point R, due to two things. One, all the nuclei in the system. Each nucleus has a nuclear charge, okay, and that creates an electrostatic potential at every point in space. And then the electrons have charge, and so they create an electrostatic potential. And so equation 13, if you know a little quantum mechanics, actually makes a lot of sense. Let me try to explain it to you, even if you don't know a little quantum mechanics. That first term where I sum over all the nuclei, that tells you what the contribution of all the nuclei is to the electrostatic potential at some point R, okay? And what is that? Well, it just depends on how strong is the charge on nucleus A, so that's Z sub A, that's the nuclear charge on atom A. So for example, for carbon it would be 6 atomic units. For hydrogen, it'd be 1 atomic unit, etc. So it's just your atomic number, basically, because your atomic number is the same as the number of protons. And then it depends on how far away this nucleus is. So the electrostatic potential contribution dies off as 1 over R. And so that denominator says how far apart is point R from the location of the nucleus, R sub A. And that's a vector difference, and then I compute the absolute value of that vector, so that's just the length of a vector going from RA to R, or the length of the vector, that's the difference between going from the origin to point R and the origin to Z sub A, and I compute that vector difference and then take the magnitude of it with those absolute value signs. And that's an easy calculation to do, no big deal. The electrons are harder. Why? Because I don't know where they are. Quantum mechanics tells me you don't know where the electrons are, you only know a probability of where they are. Well, it turns out that isn't infinitely complicated. All I have to do is then say, okay, fine, I don't know where the electrons are, but I do know the probability of where they are if I ran some quantum mechanics calculation and got the wave function. So here psi of R is the wave function, and it basically tells me if I take psi star, the complex conjugate of psi, times psi, that's the probability of finding the electron at some position, in this case R prime. Okay? So psi star of R prime times psi of R prime is how likely is the electron to be at some position R prime. And if it is at R prime, what is the electrostatic potential generated by that? Well, an electron has a negative charge, so there's a negative in front of this integral. And it's just negative, the electron charge is 1. Negative 1 divided by the distance between point R and point R prime. Okay, so it's very analogous to the previous term, and the only difference is instead of a nuclear charge Za, I have a charge of 1 because it's an electron, and the distance now is between some point R prime and R instead of the location of the nucleus, RA and R. And I don't really know the electron is at point R prime, so I have to get the probability that's the case, so that's psi star of R prime times psi of R prime. And because the electron could be anywhere, I have to integrate this over all possible locations R prime, so that's what the integral is doing for us. And you'll notice you're integrating over R prime. So that's it. That gives me the electrostatic potential at location R due to the nuclei and the electrons. Now, so what? That doesn't give me a nuclear charge. That gives me an electrostatic potential. But in the restrained electrostatic potential procedure, RASP, which was invented in '93, I read this paper when I was a grad student, the argument goes like this. If I know the electrostatic potential, because of equation 13, let me make up atomic charges that are going to be charges that are centered on all the atoms, and I'm going to pick those charges such that I minimize the error in the electrostatic potential. So I have a correct electrostatic potential in equation 13 if I've done quantum mechanics and have psi, and I will pick atomic charges to best reproduce the electrostatic potential over space. And I have some procedure to try to figure out what the error metric is, and I keep tweaking the charges and minimize the error of the electrostatic potential compared to equation 13. Okay, that's one way to do it. There are other ways to do it. I just mentioned that as an illustration, and because that is one of the popular approaches. Now, what's the computational cost of these electrostatic terms? Well, I mentioned for the van der Waals terms that apart from things that are bonded where you don't worry about those, you have basically for every atom, you have the electrostatic interaction with every other atom, okay? So there's a lot of those. They're basically, if they're n atoms, there's something like n squared over 2 terms, which can be very, very large if n is large, prohibitively large. For the van der Waals terms, if you feel like you need to, and you usually do eventually, you eventually cut them off at some long distance. Why is that? Well, this thing decays for the van der Waals as 1 over r to the 6th. So if you have 2 atoms that are 100 angstroms away, then 1 over r to the 6th times that if for r equals 100 angstroms is basically going to be 0. So you don't have to worry eventually after some long distance. And we can argue about how big that distance is. It's certainly closer than 100 angstroms that you could cut it off. A lot of times people cut it off at more like 10 angstroms and say the error that we're making is small due to this. The problem with the electrostatic terms is that they die off quicker. They die off as 1 over r. So 1 over r is still maybe important at 10 angstroms, even if it's already gone to 0 for the van der Waals term. So a simple cutoff, you can do it, but your cutoff distance is so large that the calculation can still be painfully slow. There are approaches to do this. Some of them are pretty well advanced by now. There are things like particle mesh Ewald as a way to do tricks with Fourier transforms and get the long-range electrostatics right without just sort of brute force cutoffs. And those go a little beyond what we're talking about, but those are implemented in state-of-the-art codes and are pretty important because otherwise the electrostatics would be the rate determining step. If you use these particle mesh Ewald and other long-range summation techniques, then the dominant cost would then fall back down onto the van der Waals terms.